Thanks, Adam. Hi, everyone. Okay, so I like having extremely interactive lectures. Please interrupt me with questions at any point and at any level. And as a warning, I give comically thorough answers. So if you ask me a question, I might give you the history of something. Okay, so we're going to talk about deep learning for this next section. And so I will say that as part of this, we're going to take a second look at kind of these concepts of machine learning, but I use a slightly different terminology. And I think it's really helpful just to hear these same key facts, but in a slightly different language. Okay. And then specifically the example that we'll be focusing on is something called a multi-layer perceptron. So we just learned what a perceptron is, and now we're just going to glue a lot of them together. And it turns out that's what makes up a neural network. At the end of this, although we don't have too much time, I'm just going to mention some other neural network architectures that exist and really explain where does the quote unquote diversity of these neural network architectures come from? Like, what does that mean to build a convolutional neural net versus a multi-layer perceptron? So I always start my understanding of really any model fitting with this kind of silly, this silly mnemonic mu, which means that when we are just trying to solve a problem which requires fitting some data to a model, I have 3 ingredients that I'm allowed to play with. The first ingredient, and I'm going to go through this. Let me make sure. Yeah, I'm going to go through this first using kind of our more formal physics way of thinking. And then I'm actually just going to say the slide again in a data-driven way. And so the M stands for a model, where I'm a transient astronomer. So I think a lot about supernovae, but whatever field you're in, we're familiar with models. That's what we do as physicists. We write down the physics that we think are governing the observables around us. So I might write down a model to describe the light curve of a supernova. And that model has some free parameters. And I want to tune those free parameters so that my model looks just like the data that I see. How am I going to answer the question, this model looks quote unquote good versus bad? Well, we normally write down a number or an objective function, our first O, which literally quantifies that idea of good or bad fitting model, where the most standard one that we often hear about is called chi-squared. And chi-squared we know is just model minus observation squared and some extra factors we don't care about. Okay, well, I don't just sit there all day and try different values of my model, see which one is good, and then keep going. I like to have a smart algorithm that thinks about how to tune those parameters for me to find the best model, where again, best means that I optimize an objective function. So that last step is my optimization method, the last O of mu. For that, what you guys actually just coded up is called gradient descent, and we will look at it again in a slide. Any questions on mu? Excellent. So let's say this again in machine learning terms. Models are still models. One difference, though, is that as we've just seen, I'm not writing down physics by any means. I'm writing down basically just matrices and vectors. So really a data-driven type of model where I'm still going to tune the different values in those vectors just like I would in physics, but I'm not inputting any physics from my vast domain knowledge of the universe. My objective function can still be something like chi-squared. But as you've seen, the wonderful thing about machine learning is that it can also be kind of anything. If I work at, what's a not evil tech company? I don't know. Let's say Uber, and I'm just trying, I don't know, Uber's not that evil, I think. Anyways, let's not go on that. But pretend I'm at Uber and I'm just trying to minimize, I'm trying to optimize money. That can literally be my objective function. Sure, within that objective function, maybe I'm minimizing how much gas I'm using, or I'm maximizing the passengers I can fit. But at the end of the day, I can write down any function I want, and I'm just trying to optimize it. It doesn't have to be statistically interpretable. It doesn't have to be things like chi-squared. It can really be whatever we want. And we're going to play with that concept. And just like what you guys just did, I think we were optimizing accuracy instead for a classification task. I will say that optimization methods for what we're going to think about neural networks is the same. We actually still use gradient descent, and we'll talk about why we end up using that, because it turns out it's really helpful for our problems. Any questions on revisiting Mu with a kind of different point of view? Good, now we're all machine learners, not physicists. So here's a really simple data-driven model. I think linear models are machine learning because there's no physics being put in. We have lots of flexibility, and our choice of what this model looks like is guided by the data itself. I don't think this isn't terribly important, but I just like pointing out the fact that what we already have talked about, the fact that multiplying some free parameters by some features, so whether that be x to the 0, x to the 1, x squared, or features of variable star light curves, that multiplication in sum is simply a dot product if we think about it in vector algebra, which we don't have to do if we don't want to. But in our physics language, I might call these free parameters, and maybe I'll call these guys features or independent variables, and then my output is a dependent variable. But now in our new machine learning language, I would consider these not features, but quote unquote weights of my model. There's no difference between the two. Weights aren't something special. They're just free parameters of a neural network or any data-driven model. So, like we said, the objective function can be literally whatever we want in many ways. In this case, I'm showing mean squared, it's not quite mean squared error, but it's close enough, it doesn't matter, divided by n, and it is. Something like the model minus the data squared, sum that up. But you can also think about adding terms if you want to constrain your model in some way. Can you raise your hand if who has seen Bayesian statistics before, so I get an idea? Oh, good, a decent amount. If you haven't, that's totally fine. We're gonna actually have Bayesian statistics with Vanessa, so I apologize for slightly out of order. But if you are familiar with this, you might recognize that this first term is what comes out of just a simple likelihood of a, there's a question, go ahead. That's a squared. The question is a superscript squared or a label, and it's a squared. Yeah. Anyways, okay. So you might recognize this first term is literally just like a simple maximum likelihood, or if you're not familiar with that, it's like chi-squared. But then you can think of this second term as a prior. And specifically, this prior is saying, hey, these parameters I have called beta had better be really tiny, because this additional sum is telling it, I'm going to penalize you whenever you make these too big. In machine learning words, we don't call it a prior, even though it plays the same role. We call it a regularization term. Good. And finally, this is what we just coded up actually, but now we're seeing it graphically. The way that we optimize is with something called gradient descent. So this plot is obviously a cartoon, but it's showing you on the x-axis different values of a model parameter, whether that be the slope of a line, one of our beta values, it doesn't matter. But for every different value of our model that we have, we can plug it in to our objective function or our cost function and see how well our model is fitting our data. And the point of gradient descent is to say, let me start at some random guess for the model values. And then I'm going to figure out which way is the slope going. In this case, it's clearly pointing down this way. And just like a ball rolling down a hill, I'm going to follow that slope. And I'm going to take a step in the same direction as the gradient. I'm going to then check what's going on. I'm going to see if that gradient's gotten bigger or smaller. It looks like it's gotten a little bit flatter, so smaller. And so I'll take a little bit of a smaller step because I'm going to try to match that gradient. I don't want to be kicked too far. I keep taking those steps until I see that my gradient is 0, which means I must have reached some sort of minimum. And because I'm trying to minimize cost in some way, I must be at the best fit values. That's how our gradient descent works, and that's what you just coded up. Any questions about that? Okay, so now that we are very familiar with the Mu framework, it makes sense. It makes, I think, hopefully more sense of where neural networks slot into this. Neural networks are just a model. And so we're going to explain how they work, but then we're going to optimize them by defining an objective function just like we would with any other model, and we'll optimize it with gradient descent. And we don't need to mention what stochastic is right now. Okay, so what is a neural network? This is my attempt at a description, although I think it doesn't make sense until we go back and look at it. A neural network is it's essentially a piecewise function that you are trying to make pretty complicated, a complicated piecewise function, but built on these little Lego blocks of relatively simple function. And by adding lots of these simple functions together, we can approximate almost any nonlinear function. That's kind of the beauty of neural networks. So how does that actually work? So I realize you had a perceptron lecture, but we're going to revisit it anyways in slightly different words. So this is not a perceptron. This is just a graphical representation of that model we've already looked at. So our free parameters are called beta, 1, 2, 3. And then our features are called x, x squared, and x cubed. And what this graphical model is showing us, just like in the perceptron model, is that I am going to, for each edge of my graph, which I will highlight, this is an edge, it means that I will multiply the feature by some tunable parameter, and they all come together representing a sum. So this graph represents this model. Okay, now pretend I did something kind of weird. Instead of feeding the sum of these 3 guys directly into my observable, I am going to kind of insert this extra layer of free parameters. So in particular, I'm going to have this new parameter called H1, where, okay, I have 3 free parameters, which represents the weights, and the sum of them give me a value here. And I'll do the same thing. I'll call it H2. So these are kind of different combinations of these 3 ingredients. And then to finally get my actual observable parameter, I will take a combination of these 2 ingredients with other tunable weights. So this is a really, really silly thing to do. Don't do this. The reason why is because these 2 things are completely degenerate with each other. Like, I don't gain anything by adding 2 extra variables. I'm just making it complicated for complexity's sake. However, this is the graphical representation for a multi-layered perceptron, which is the most basic neural network that you can make. So what in the world is the difference between this thing that I just called silly and this thing that everyone's using? The answer is that something funky happens with these 2 variables I've defined, and they have an H because I often called them a hidden layer, something I don't actually observe, but I'm going to use it as a tool to help me predict the final thing that I do observe. And in particular, I transform this linear model, and by that I just mean it's a linear combination of different features, into a nonlinear model. So if we zoom in to one of these nodes, which I'm now going to call a neuron, it's actually doing exactly what you just coded up. I'm going to do my dot product where I have, again, sorry, I clearly stole this from the internet, so I changed the constants a little. The features here are X, 1, I, and N, and the betas are now changed to W's. But the point is that it's just a dot product between tunable W's and the things I observe X's. And I can or cannot have bias. For the record, from now on, there's no bias. It's always 0. We're never going to think about it again. So now, the trick of a neural network and your perceptron is the fact that I pass it through this nonlinear function. So now instead of having a really simple linear model, I'm having a piecewise combination of lots and lots of nonlinear functions. And it just turns out that from a theoretical basis, by doing this, I actually can, like I said, approximate any, within reason, nonlinear function. And kind of the beautiful thing about this, well, let me be more clear, is so this is the most commonly used function, which is called a sigmoid function. That's, okay, good. That's this guy down here. And it's kind of exactly what you guys were just using, right? It's this idea of, okay, if I'm less than a certain boundary, I'm going to be equal to 0. But if I'm greater than a certain boundary, I'm going to be equal to 1. There is a little bit in between where I have to smoothly get from 0 to 1 so that I can take the derivative of this function. But that's all the little S shape is doing. So people use this function historically because neural networks were inspired by the brain way back in the day. And we thought that this is how neurons work, is that they have some activation potential in which they're either emitting kind of 0 electrons or they're emitting N electrons. It turns out this is like absolutely not how brains work, and we don't need it to be a sigmoid function by any means. We just need it to be any nonlinear function. And so actually one of the most common ones is the ReLU function, which is literally the least nonlinear you can get. It's this idea that it is a linear horizontal line until some number, and then it becomes a linear one-to-one line for some number. This is technically nonlinear. It has this little piecewise component to it, but the derivative is defined almost everywhere and is so cheap to figure out. If I'm over here, my derivative is 1. If I'm over here, my derivative is 0. I'll admit it's not defined at this specific point, but our neural net hopefully will never get to that specific point. So this inclusion of a nonlinear function is really what makes a neural network possible. Are there any questions about that? Okay, then we've done it. We have mastered neural networks. So the question is, in the exercise we just did, the output was a Boolean. It was 0 or 1. However, in the framework I just introduced, it's clearly not a Boolean. So what's up with that? And I responded that we are going to, was that a fair representation? Okay, so I responded that we are going to figure out what's up with that in a few slides. Inspired by this question, let me step back and point out the fact that the range, so the domain, as in the acceptable X values of all these functions, is -infinity to infinity. I can plug in anything. But the range, or the output, is not -infinity to infinity for these functions. And you want to think about what activation function makes sense for my problem. For example, if I'm trying to estimate the mass of a galaxy with a neural network, I had better not use a sigmoid because the range is limited to 0 and 1. And galaxies can be greater than 1. And so you do want to have some considerations here, but that flexibility is on you, is kind of the amazing thing. And so we are going to play with that in the notebook a little. Okay, so now the slide on a pop quiz. Talk to your neighbor for a second to guess or correctly estimate How many free parameters are represented in this neural network? And there are no biases. Biases don't exist. Okay, let's come back. Does anyone have an estimate for how many free parameters there are and why? And okay, go ahead. Sorry, so assume that there are 3 inputs, xi, x1, and xn. Yeah, so why are there 12? That's right. That's right. So in a way, we're just counting the edges, right? There's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Exactly what you said. Are there any questions on that? Are there any questions on what we've talked about? Good. Okay, so deep learning, which you've heard so much about, and I am not exaggerating, is adding more and more hidden layers. So just having more series of connections, which add new nonlinear neurons between the things that you observe and are inputs and the things you're trying to predict, which are outputs. That is literally all deep learning is. Good. So we've solved that. So then why is there kind of all this hullabaloo about deep learning? So the different quote unquote architectures that you hear about really are just referring to things like how many neurons am I adding in each layer? 4 or 2 or 10? And how many layers am I adding? You can also play with things like the inputs, the types of inputs you're giving it, and the output types. One of the neural network architectures that we're going to spend a lot of time talking about tomorrow is called an autoencoder, where its goal is going to be given the same input or given an input as your output, predict exactly the input I gave you. And we'll talk about why you would ever want to do that and why it makes sense to do that. And then the last thing is that you can play with the way that neurons talk to each other and exactly what neurons do. They don't just have to be this simple nonlinear function. You can do some funkier things with them, although we're not going to touch too much on all of the things you can do.
Hey, Ashley, we have a question from the Slido.
Yeah.
Could you elaborate on the choice to use nonlinear hidden layers?
I think I need clarification on the question.
Yeah.
Sorry.
Questions on the Slido are anonymous, so if somebody
Yeah, I know.
Yeah. If somebody wants to speak up and volunteer your question with a little more clarification.
Yeah, or if you want to resubmit, my misunderstanding is just coming from, are you talking about like why include it in the first place, or the decision on how you can manipulate hidden layers, as in how many neurons to add? Yeah. Yeah, okay. So the question's been clarified. Which is basically explain why in the world you do this. Like that's kind of it with a few more details, and I will do that now. So if I just wanted a linear model, pretend I didn't do any of this like silly neuron business. Part of the issue is that without talking about math too much, I'm just really limited in what I can do. And like one example that you can think about is, imagine I have a classification problem and I have some 2-dimensional feature set. Sorry, I only think about supernovae. So imagine it's like duration and brightness. And for whatever weird reason, type 1As like to sit right in the middle of that plot, and type 2s like to sit a circle, an annular ring around that circle. How would I draw a line to divide those two classes? I couldn't. What a neural network can help you do is figure out a nonlinear way to split up those features and do that classification for you. Does that clarify somewhat why you would want to do this? And then a good rule of thumb, although it's very much, a made up rule of thumb, is that the deeper you add, as in the more layers you add this way, so the more dot products we're doing and nonlinear function activations, kind of the more and more complex features you can represent in this neural network. If you only have one layer, you're only limited to a few piecewise functions, but the deeper you go, the more and more complex you can make it. And that's why people turn to deep learning. Great. Any other questions? Okay. So some example inputs, and I really mean the fact that you can do anything, which is kind of amazing. If I had one-dimensional data, which is what we were kind of playing with, all of our features I was describing were just powers of x, like x squared, x cubed, etc. But I can also feed in just in a sense, my raw data. And exactly like Adam mentioned, when our brain looks at an 8, we know it's an 8 and we don't have to think about it. The beauty of a neural network is that you don't need to design interesting features. It'll just do that part for you. And so you can just directly input something like a picture of an 8 and it can learn what that looks like. And then the last thing, which is actually what you are going to be using for your example problem, but as an output, is a categorical type of representation of your data, where let's say you have different types of galaxies, 2 classes, ellipticals and spirals. Instead of typing in the words elliptical and spiral, you can represent that as a 2-dimensional vector, where the vector is equal to 0, 1 if it's an elliptical, or 1, 0 if it's a spiral. That's called a one-hot encoding, meaning that I'm going to have a vector that represents every possible class, and it'll only be equal to 1 for where that class is true. So you can be really clever about this and really have whatever you can imagine can be an input or output to your neural network. Okay, so we need to actually now train or optimize our neural network. To do that, as we know from Mu, let's specify an objective function. And as we mentioned, the beauty of neural networks is that we can be as flexible as we want to be. For a classification problem like the ones we've been working with, one of the most common objective functions to choose is called cross entropy. We don't need to explain why. Well, I guess we do need to explain why. I didn't capitalize this. So here's the issue, and this is kind of what someone pointed out. So in our problem, our output was only a Boolean, 0 or 1. How in the world do I take my gradient of a 0 or 1? I can't. So I need to figure out how to do that. And so one thing we're going to do instead is, okay, if I can't make a vector that's 0 and 1, why don't I make it a probability vector that comes out? So that, okay, when I see a new galaxy, I can say 0.3%, not 0.3%, sorry, 0.3 out of 1 chance that it's elliptical and 0.7 chance it's a galaxy. There's a specific constraint on a vector like that. It has to add up to 1. And that's kind of it. Otherwise, and I guess it has to be greater than 0. That's true too, or equal to 0. So how do we guarantee that it's greater than or equal to 0 and that it adds up to 1? People are so clever about this and they figured out a way. And that's cross entropy. This is specifically called categorical cross entropy, where, okay, my neural network can spit out any ridiculous vector at once. And then what I'm going to do is take the exponential of that vector. why does the I think have a discussion with your partner about how this cross entropy function satisfies the two properties of a probability vector that we just discussed. But remember, those properties are that it sums up to 1 and that's greater than or equal to 0 for every element. Okay, let's come back. And I won't ask to share. I will just point out the fact to explain in words why this makes sense. So my denominator is the sum of the vector for all the classes where I'm taking the exponential. And by dividing by that sum, I guarantee that the sum is now always equal to 1. Specifically, the numerator is telling me the probability for that specific class, the correct class. So my cross entropy, in a sense, is just trying to optimize the probability that I got the class correct. Questions? Good, good, good. For regression, which we're not doing right now, this is a great example of a regression objective function that we've actually already looked at, right? It's looking at the sum of the residuals squared. So I think we understand that. And then it's looking at this thing that is a regularization term, which acts kind of like a prior in Bayesian statistics, but it's a little bit different. But now we're saying, hey, the weights of my neural network had better be as small as possible. The reason why this is actually really common in deep learning is because there are lots and lots of solutions. There's no best solution to a neural network. Whereas where we're trying to fit a model of like cosmological inflation or something, and we want to make sure we get the right solution. In machine learning, we're trying to just do as well as we can do, which means that we're trying to find a local optima versus the global optimum. Not the best solution, but just a pretty good one. And so we often add regularization to help us not look everywhere for the solution, but try to hone in on just one part of our possible space of tunable parameters, or the weights. Okay, finally, let's optimize that thing. We're going to use gradient descent to optimize, which is the picture we just looked at. So we're going to try some weights. We're going to see how bad or how well we did. We're going to look which way is the gradient of the neural network pointing, and we're going to move a little bit towards that gradient. For whatever reason, machine learning has reinvented the chain rule of calculus, and they gave it a new name. They call it backpropagation. But actually, the beauty of this is that because we're using like really simple functions, right? We are using dot products and like a sigmoid. So it's so easy to figure out what the slope of that kind of Lego piece together function is, because it's just the chain rule. I just have to multiply some really easy gradients together. And that's called backpropagation in the machine learning literature. It's literally chain rule. Okay, so this is a little snippet of code, which I'm not going to actually go through, but it's to show the fact that neural networks are truly this easy. They are just a model that has a few vectors of weights you are trying to tune to be correct. You dot product those weights with some features and pass it through a nonlinear function. And then to optimize it, you, like we said, do gradient descent, which means that we calculate how well or bad we did. We figure out which way the slope is going, and then we go towards that slope. That's it. Are there any questions on that? Not on this code necessarily.
Hey, we have a question in the Slido.
Cool.
Question is, would it work to use, instead of many hidden layers with nonlinear action functions, one long input layer, but use things like sine, log, etc., instead of only x, x squared, etc.?
Yeah, so the question is basically, instead of having a neural network, can I use these nonlinear features? And the answer is, in many ways, yes. However, if you do that, again, you're only going to be limited to linear combinations as like addition and subtraction of those features that you've designed by hand. So if you're going into a problem like classify an 8 and you don't know what features to use, a neural network's helpful because you don't need to figure out those features. It will do it for you. So it is true. You can always figure out, well, you can very likely figure out features that are hand designed to probably do as well as a neural net. But the beauty of neural nets is that you can skip that step. Okay. Let's see. Okay, so we're at the end of the time I'm supposed to use. I have a few more slides, but they kind of now go into different architecture types and considerations. And we're not going to go as deeply into like how it works. So are there any remaining questions on how a multi-layer perceptron actually works? So we're all experts then in deep learning is my understanding. Excellent, excellent. So I just want to point out the fact, we mentioned this earlier, like architecture just means, hey, I have the freedom to like switch up the different types of neurons I'm using or switch up the inputs and outputs. And so I want to point out some other kind of famous types that we're not going to do in detail. So a convolutional neural net, I'm sure you've heard of. This is kind of the two-dimensional extension of a multi-layer perceptron. By that, I mean, in a multi-layer perceptron, I have my features and I multiply it by weights. In a convolutional neural net, I have my features, which are represented as a two-dimensional image, not a one-dimensional vector. And I learn instead of a vector of weights, a matrix, so a two-dimensional vector of weights. And specifically, I convolve this two-dimensional neuron with my data to learn interesting nonlinear features of my input data set. And then the output, again, can be like whatever I want it to be. I can try to classify them. I can try to, from the picture, estimate how boaty it is or something. I can do whatever I want. Recurrent neural networks, which is a really other common type, but we're not going in detail. But I hear that you did time series in your last session. So these are kind of the go-to for time series, where the only difference is instead of my neuron having a single nonlinear function, it kind of just saves two nonlinear functions. One combination of the inputs is saved as kind of this idea of, what should I guess next? And then there's a different set of those inputs that's saved as a function that's more answering the question of, what have I learned about everything else I've seen? So that every time I see something new, I can go to that second part of the neuron and ask like, hey, what have the other inputs taught me about what I'm trying to do? As an example, when you're typing to a friend, and nowadays it's really common to have predictive text where it's trying to guess your next word, you may notice that it does better when you have part of the sentence already filled out. And that's because they're using something like recurrent neurons to say, hey, what has Ashley already said in this text? And use that information to help you predict what she wants to say next. Oh God, I forgot I added this. So this is called a generative adversarial network. They are falling out of style a little bit, which is why I had my little exclamation. Just like this, I think this is a really fun example though, of like how creative this community is. The idea of this is that, okay, I've made a multi-layer perceptron, and its job is going to be to take in images of cats and let me say it a different way. I have a neural network, multi-layer perceptron. Its job is to classify images of cats to the best of its ability. So it's either cat or not cat. And then I'm going to actually make it directly compete with a second neural network, a multi-layer perceptron, whose job is to make images of cats. And so one of them is going to try to discriminate whether or not that cat is a real cat or just a fake cat from the other neural network. And the other neural network is going to try to continuously trick that neural network by making fake cats. And by using these types of networks, you get one network that's really good at determining what's a cat and not a cat, and one that's really good at making cats. And so there are scientific reasons why you might want to do this. There are some really fun applications, but they're slightly falling out of style for some reasons that I don't have to go into.
Except that somebody online asked, why are GANs falling out of style, and a sad face emoji.
Oh no, sorry. If anyone's using GANs in research, they're not falling out of style. They're great. So it's a little hard. I think it's going to be a lot easier to explain the answer to this question after we have our lecture tomorrow, where we learn a lot more about what's called dimensionality reduction. And it just has something to do with the way that it's learning. Actually, I can summarize it quickly. It can be really unphysical. That's like the issue, is that you can't interpret what these things are doing by the way it's constructed. But you can be a lot more clever about constructing your neural network so that it is interpretable. That's kind of the main issue. Oh man, okay. Now this is just like gossip at this point. So I do like to bring this up because we're at a really weird point in machine learning where there's kind of a fight to be the one and only machine learning package in Python. And so I think it's worthwhile just to point it out so that if you're ever at like a fancy dinner party or something, you can have a strong opinion on this. And so in the case of Python, I think we know this. Modules kind of represent like code that someone has already done the hard work of writing for us, and now we can just use it to our heart's desire. Where we think of things like SciPy and NumPy as like the go-to modules for things like scientific computing and mathematical computation. So there isn't exactly one for neural networks yet. The one that we're using in this lecture series is called PyTorch. It is currently the winner, as in it's one of the most popular. And if you get to the point where you're following machine learning literature, it's the one that people are publishing their code in. All of these are like, they have like hilarious histories, and they're largely all from private companies that have made it open source. So PyTorch is from Facebook. Does anyone have an M1 chip? Oh no. Okay. So I do want to warn you that our notebook, I've recently learned, it might not work on M1, and I'll explain why. PyTorch natively works on M1. Thank goodness. And for people who don't know what that means, M1 is the new, it's the new computational chip from Mac, and it just doesn't natively work with a lot of these modules yet. So the one that actually is my personal favorite, but sadly is not winning, is Keras. And I've specified here it has a TensorFlow backend. That just means that all of this weird linear algebra is being done with TensorFlow, but Keras is the thing that's letting me click together different types of neural networks to make any architecture I want. It's open source, although TensorFlow is from Google Brain. Unfortunately, though, just due to the way that this has been built, it's like they're just attaching more and more complex little features onto this poor little code. And so it's really falling out of style for that reason. It's also very hard to get to work on M1. This is unfortunately, I didn't realize one of the modules that we will use for our Jupyter notebooks does rely on TensorFlow. So I will work with you if it's not installing correctly, or you can just directly do all of this work on Google Collaboratory, and I can help you set that up. And then last, I'll just point out, and Vanessa will talk about some version of this, although with PyTorch, people are really moving towards having like really interpretable machine learning. And by interpretable, I mean that as scientists, we don't just want to know the answer, we want to know how certain we are. And that's called probabilistic deep learning. And those packages are really, really new, and there's many competitors. Some of them include things like JAX, NumPyro, and Pyro. JAX is a pain to get on the M1, but we're not using it. Okay, so that is the end Are there any remaining questions before we get to the notebook?